Hi, it's time for another math easy. So we're going to discuss just part 2 of the properties of the definite integral series. You can see the part 1 of it in the video link below. Basically, this definition of the derivative here, integral of a to b of fx dx, it just equals or defined as limit n goes to infinity of the sigma notation fxi times delta x. This is just a sum of infinite rectangles, and the delta x is the width of the rectangles, and just b minus a divided by n. You can see in the video link below on the intro to the area under graph equations. Basically, I'll describe this in more detail. But basically, let's look at property 1 of this video series here. Basically, this one here, it's if you have an integral of a to c, in this case of fx dx, plus from c to b of the same function here, and then this just equals, well, the integral from a to b here. So this is kind of doing intervals of the integrals here. So the proof is a bit complex to do, but I can show visually why this is true. Yeah, so if I draw the axis here, if I just draw a random function like this here, this is f of x, and let's say in this case a here, we'll call this is a, and then this is b in this case. I mean, this is b and this is c here. So then basically the number of the integral is just the area under the curve. So this one here, this corresponds to this area, and then this from c to b is just this area here. So we'll just do it like this, and then it just equals the total area here. So this is just from a to b here. So this visually you could see that it should work. So that's just a visual proof for that. Yeah, so now to illustrate the above property here, we'll just do this example here. So if you're given that the integral from 0 to 10 of fx dx is just 17, and then but from 0 to 8 is 12 here. So what's 8 to 10 here? So this one, you can just write it down because this is within this interval here. So you can just write it down as exactly like the above property. Yeah, so if I write it down here, you're just gonna 0 to 10, the integral from 0 to 10 there equals to the 0 to the 8 fx dx, and plus the one we want to find out, which is 8 10 fx dx. And we know what these ones are. This is 12, and that's 17 here. So this is 17, this is 12, so then we just have 17, we'll just subtract it by 12 here, equals to this one here, 8 10 fx dx, and this just equals to 5. Yeah, and this is just to illustrate it quickly there. Okay, so now let's bring us to the next properties I'm going to show here. But these ones here for the next 3 are only for this one here when a is less than x, or less than equal to x, and x is less than equal to b here. So it just means that you're not going to have, let's say, 10 to 8 here or something. And in the above property, it doesn't matter what you have in this case here. But for this one here, so let's look at property 2 here. Basically, if f of x is greater than 0, then the integral from a to b, remember a is less than b in this case, of fx dx has to be greater than 0. And this one is it's pretty easy to see visually. You're just going to have, this one's going to be above 0 everywhere. So then the integral is going to be a positive number, which is the area under the graph here. Okay, so now property 3 here, this one just states basically if f of x is greater than g of x, then the integral of f of x has to be greater than or equal to the integral of g of x. And this one is pretty straightforward, because if you just look at this one here, if this is f of x here, and yeah, if that's f of x, then if it's always greater than or equal to g of x, so g of x would be something like this one, like this. And this is g of x here, so when it's never greater than it, so the integral, which is the area under it, has to be less than the one above. So this one's pretty straightforward. Okay, now the last property that I'm gonna get to today is basically property 4. If m is less than f of x and it's less than m, and these ones are both constants here, or so they're both constants, these m and capital M, then basically m times m minus b minus a is less than equal to the integral of fx dx from a to b, and it's less than equal to capital M times b minus a here. And the proof for this one, well, you can just look at it visually here, or look at my other video on the property of why this is m times b minus a, which is basically the integral of a constant. So if you were to graph it out here, this is x, this is y here. Let's just graph, because m is a constant, so we could just draw a straight line. This is m, and then capital M should be constant as well. So this is capital M, the function here, and then f of x is varies, so it'd be something like this, etc., etc. So this one is f of x. So then from a to b, let's call this a, this b here. So remember, it's always the area under the curve is the integral here. So then this area right here, this area, because remember this area of a rectangle, this one is just m times or the height times the base here, the base times length. So that's the area of this one here. So it has to be, so then this function here, this fx, has to be greater than it. So if we could just draw this b across, this a across here, so then this area, this entire integral has to be greater than, yeah, so that's this one, fx dx has to be greater than this one, and then it has to be less than the entire area in this case here. And this one is just basically, because remember, this height is m, and this is b minus a. So then that's just the area of the entire one, and that's greater than or equal to fx dx, depending on whatever this function was. So that's the proof for this one here. Okay, so now this brings us to the last part of this video. Just an example 2 here. To basically, we're going to use property 4 to estimate the integral of 0 to 1 of e to the negative x squared here. So if you were to graph this out, yeah, so if we graph it out from 0 to 1 here, this function is decreasing here because it's to the power of negative x squared. So if you put let's say infinity, you're going to be negative to the power of negative infinity. That goes to 0, and etc. So now let's just plug in. So if it's always decreasing, so then let's just plug in the endpoint. So if we put e to the negative 0 here, so e to the 0 is equal to 1. You see the video link below on basically on power functions. So that's 1 here, and then at 1, if you plug in the endpoint there, e to the negative 1, this just equals 1 over e, and this is roughly, yeah, roughly 0.3697 or whatnot. We'll just write that down. Let's just put it somewhere far here. So this is 1 over e, and it's always decreasing because whatever the greater the number you put in, it just gets smaller and smaller. So it would look something like, actually, I'm going to say this is a 1. So this is a 1. This height is going to be 1 over e. So this is 1 over e right here. So it's always decreasing here. Well, it may not look something like that, but anyways, it's decreasing. So from this right here, we have that it's, so from property 4 here, if this is f of x, and then we could let this one be little m. This one could be equivalent to little m here, and this is equivalent to big M, because if we just draw it all the way across here, and as you can see, if you draw the rectangle across from there to there, this one, this length is 1, this is, and this height is 1. So then the capital M, let's just say it's capital M is that, and this is little m here. So now from property 4, we get that, yeah, that basically the area of this rectangle is less than the area under this f of x, or the integral here. So we're just going to get 1 over e, we'll times it by 1 minus 0 here. So we'll just go 1 times, yeah, so we don't need to even write this. So we go 1 over e is less than equal to the integral, which is the area under this entire curve, fx dx, from 0 to 1, and it's less than equal to 1 here. So we have an estimate for this. So this is in between, yeah, it's basically in between this one, 1 over e, which is 0.36 something, yeah, 79. So it's between 3679, just we'll plug that in there, and less than 1. So we have a rough estimate there. Well, yeah, that's all for today. That's all. You can download these notes in the Dropbox link below if you learned a thing or two about integrals and their properties. And yeah, just stay tuned for another math easy solution.